It's my great pleasure to present our good friend and very good researcher, Professor Maria Alessandra Ragusa from Italy, and she will speak about the title on the screen. Thank you very much, Professor Ragusa, for agreeing to deliver a lecture at our seminar, and please go ahead.
Thank you very much to all of you. I would like to start my talk thanks to Professor Alexey Karapetyants, that is the deep friend and colleague, but first deep friend. And he was here in Catania invited by me, and I was honored to have him. So I thank you so much to this warm invitation. And now it's time to start. And of course, thank you to all of you to be here. Thank you so much. My talk today is dedicated to the functional analysis and method of PDEs. Aim of the talk is to study regularity of the action of some integral operators and also commutators in the objective to obtain regularity properties for solutions of partial differential equations and also systems having discontinuous coefficients. Of course, I point out that it is a gap from constant coefficients, continuous coefficients, and discontinuous one. So the interest that I have is to study regularities for PDEs and systems having discontinuous coefficients. Well, firstly, I wish to show the main actors of this talk. These are the Morey classes and the VMO classes. First, we start with Morey spaces. So let us consider P between 1 and infinite and lambda between 0 and the dimension f. F is a real measurable function in an open-bounded set that we call omega, containing in n more or equals 1. So, if the absolute values of f with exponent p is summable in omega and the set described by this quantity 1 over rho with exponent lambda integral in omega cap bx rho of f with exponent p, where rho is between 0 and the diameter of omega, x is in omega, is upper bound. So we say that f belongs to the LP lambda space or the Morey space LP lambda. So this is the main actor that we will use through all the talk. So if we have f in LP lambda, we define this quantity, the supremum for x in omega and rho between 0 and the diameter of omega of the above mentioned quantity as the vector space, and we say that the space LP lambda is a normal complete space, so is a Banach space. Well, similarly of what is done in the case of LP, we easily consider for the weak LP. So now we can consider the weak Morey spaces LP lambda omega, but are not so interested of our later discussions. Just a brief talk of these weak Morey spaces, then we can define later the regularity results in this class. So let us consider rho between 0 and the diameter of omega, x in x0 in an element of the set omega, and the supremum is t is more than 0, t with exponent p multiplied by the measure of the space where x is in omega cap p x rho, such that the absolute values of f is more than t, then this is less or equal a constant c independent of f multiplied by rho with exponent lambda. So this is the weak Morley space, weak WLP lambda. Now we give the definition of the subspaces of it that we are interested in. For every function f that is in LP lambda, we set eta with exponent p as the supremum if x is in omega, rho between 0 and r, of 1 over rho with exponent lambda, the integral in omega cap bx rho of the absolute values of f with exponent p. So we say here we point out that r is the values of the function eta and is the maximum of the integral of the interval 0 r. Well, we call this as the modulus of the Morley, the modulus of Morley of the function f. Well, if this quantity tends to 0 as the radius of the ball, we say that f is in VLP lambda or is in the vanishing Morley class. Equivalently, the limit if r tends to 0 of eta r is equals to 0. Well, so f is in LP lambda if this quantity here is only bounded. F is vanishing LP lambda if this quantity is not only bounded but tends to 0 as the radius of the ball. If f is in LP, the quantity omega sigma as the supremum if E is a subset of omega with measure less or equal sigma, and the integral in E of f with exponent p 1 over p is called modulus of absolute continuity of the function f with exponent p. Well, let us now study the comparison with other functional spaces because it is important that we consider one class but related with the other one. So let us illustrate some inclusion relations between Morley spaces and other spaces known in literature. The first, very simple, is with LP. So what is the relation between LP lambda and LP? It's easy or immediate to prove directly by the definition that if a function is in LP lambda, it is also in LP. So LP lambda is a subset of LP. The theorem below shows the relationship between some LP and LP lambda spaces. First of all, if we consider P and Q two quantities precisely P more or equals 1, less or equal q, less or equal infinity, and lambda and ni more or equals 0, such that are satisfying this inequality here, lambda minus n over p less or equal ni minus n over q. Then the relationship between two Morley spaces is the following one. LQ ni is contained in LP lambda. So if you see a sort of balance, we have that Q go down from Q to P and lambda goes up. So this is a relation, and this is possible to prove using nothing else than Hölder inequality. An useful particular case is the following one. If we have that U is in LP, P more than n over 2, not every P between 1 and infinity, but only P more than this quantity n over 2, then U is in L1 lambda omega, where lambda is a suitable one and is between n minus 2 n. Well, so another useful space, another actor of this talk is the space I announced, VMO. But firstly, we have to define a biggest one that is named BMO. BMO means bounded mean oscillation. And then we define the VMO class. VMO class was firstly defined by John and Nirenberg in the paper published in Communications on Pure and Applied Mathematics in 61 on functions of bounded mean oscillation. Now we are ready to define this class. Let U locally in L1 and Q a cube with sides parallel to the coordinate axis. Let us set UQ is as the mean integral of U in this cube Q. So 1 over the measure of Q, the integral over Q of the function U. Let us now define the supremum where Q ranges in the class of the cubes defined above in Rn of 1 over the measure of Q, the integral over Q of Ux minus Uq. Let us consider this quantity. If this quantity is finite, we say that the function U is in BMO or equivalent that U has bounded mean oscillation. This is a sort of definition of continuity, if you see here, but this is not a continuity because the quantity UQ is the mean integral of f. So it's not a continuity, but could be similar in some sense. Well, just recall the space VMO. If this quantity is finite, f is in BMO. Before we define the VMO class, we consider an important inclusion. L infinity is strictly contained in BMO. So, we think that it could be interesting if the function is strictly in L infinity and not in BMO. Let us prove this. Let U be a bounded function and Q a cube with sides parallel to the coordinate axis. So we have that 1 over the measure of Q, the integral over Q of Ux minus Uq is less or equal 1 over the measure of Q, the integral in Q of the quantity, the absolute values of U plus the mean integral that we put out of the integral, and because of is a quantity independent on x, is out of the integral, and so we have only UQ here. Then what we have here is the 2 less or equal the supremum, so the norm of U in L infinity. So from this chain of inequality, we have that the norm of U in BMO is less or equal the norm of U in L infinity. Now we would like to show that is strictly contained. As an example, I chose this one. The function U is 0 if the absolute values of x is more than 1, minus logarithmic of the absolute values of x if x is between 0 and 1, and logarithmic natural logarithm of the absolute values of x if x is between -1 and 0. This function is in BMO, but precisely the absolute values of this is in BMO, but is unbounded. So this proves that that inclusion is really strict. Now, I want to remark that for all the spaces before introducing, it's possible to define a local version in a natural way, so not in Rn, but in a subset of it. Now it's time to define the VMO class. Let F in BMO and let us define eta FR as the supremum if rho is less or equal R of 1 over the measure of B rho, the integral in B rho of Fy minus F rho, where B rho ranges in the class of the bolts over M with radius rho. A function f belongs to the Saracen class VMO, or we say that f has vanishing mean oscillation if the limits if r tends to 0 of eta fr is equals to 0. So now we are interested in some integral operators in Morley spaces, and we need some preliminary tools. We observe that we study the action of some integral operators in Morley spaces because these are useful in the regularity of solutions for partial differential equations of elliptic types, parabolic types, and also other, for instance, ultraparabolic types. In which sense? The sense is that if a solution is expressed as a summation of singular integral operators and also commutators, and we estimate these operators in the Morley class, we obtain the regularity results in Morley classes of the solution. So now we need some instrument before. Let us define the Hardy-Littlewood maximal operator. Let us set f be a real measurable and locally summable function in Rn. So for every x in Rn, we consider the following numerical set: 1 over the measure of B rho, the integral in B rho of f. Well, if this is upper bounded, we set mf as the supremum if rho is more than 0 of this quantity, and we say that mf is the maximal function of Hardy-Littlewood, and the application that associates to f the function mf is said maximal operator. Now we have the following implication for the weak class, the L1, L infinity, and LP. So we cover the range from 1 to infinity. Precisely, if f is in L1, we have that the measure of the set where the maximal function is more than the level t is less or equal a constant independent of f over t multiplied by the norm of f in L1. If f is in L infinity, the norm of the maximal function of Hardy-Littlewood in L infinity is less or equal the function in L infinity, and if f is in LP, the norm of f in LP of the maximal function is less or equal a constant multiplied by the norm of f in LP. In all these cases, C is a constant independent of f. Well, a variant of the maximal function is the fractional maximal function. Precisely is the following one. Let us fix eta between 0 and 1, and where appear eta is here in the exponent of the measure of the pole, 1 minus eta. Well, this is said the fractional maximal function of Hardy-Littlewood, and the function that for any f associate the function m eta is the fractional maximal operator of Hardy-Littlewood. As the maximal operator of Hardy-Littlewood has some boundedness property in Lebesgue spaces, the same analogously is for the fractional operator. So precisely we have the following result. Let us consider f in LP, p between 1 and eta, 1 over eta between 0 and 1, then m eta is bounded from LP to the weak LQ, where 1 over Q is 1 over P minus eta. So this is the relation between these two. We obtain this result considering strongly the Helder inequality. More precisely, we give a sketch of the proof. Let us suppose, without loss of generality, that the norm of f is equals to 1. Well, using Helder inequality, we have that from here, we have that this is less or equal, applying Hölder inequality, 1 f with exponent p and 1 over p, multiplied by the measure of B rho with the conjugate exponent 1 minus 1 over p. Because we firstly, in the first member, consider that into the integral it is the absolute values of f multiply the function 1. So we apply the Hölder inequality. Then we can obtain, considering all the measure of B rho here, we have that we can fix epsilon between 0 and 1. Then what we have is that we fix epsilon 1 minus eta p. We have that the first member is less or equal the maximum function of f with a suitable exponent. So under calculation, we have that the exponent is 1 over p minus eta. Then we have the supremum in the first member is m eta of f less or equal the maximum function of fp with exponent 1 minus p, 1 over p minus eta. Well, from this inequality in the previous result, we have that the norm of the set where m eta is more than lambda is less or equal where the set where m fp is more than this lambda with this suitable exponent. These are a technical calculation, but are nothing else the applying of Hölder inequality. Then we have under calculation that we can consider that is less or equal a constant, the norm of fp with exponent p, and lambda with a suitable exponent. Well, this suitable estimate can be useful to obtain exactly that. In the first member, lambda with this exponent multiplied the measure of this set less or equal constant c multiplied by the norm of f in LP. So we fix this exponent as q here, and so we obtain the requested result. So it is nothing else than the strict use of Hölder inequality. Of course, it's possible to improve the above result using Marcinkiewicz interpolation theorem. Indeed, for P and Q, as in the above result, we have that for P equals 1, m eta is from L1 to the weak Lebesgue space with exponent 1 over 1 minus eta. For p equals 1 over eta, m eta is between the L with exponent 1, the Lebesgue space with exponent 1 over 1 minus eta to L infinity. And so in the case of the space P and Q generic, we have that we use the interpolation Marcinkiewicz inequality. Another operator similar to the maximal operator is the operator that associates to every function f the function f sharp. F sharp is the following one: the supremum if rho is more than 0 or 1 over the measure of B rho, the integral in B rho of f y minus f rho, where f rho is the mean integral of f. Well, this operator was first introduced in 1972 by Pfeffer and Einstein in a paper published in Acta Mathematica. And let us now measure a result that is contained in the above mentioned paper. So, precisely, let us consider MF in LP0 for a suitable P0 more than 0 and less than infinity. Then, for f more or equals P0 less than infinity, it's possible to prove that there exists a constant c independent on f, so precisely dependent on n and p, such that the Lebesgue p norm of m is less or equal the norm of f sharp in the same space LP. Let us consider the maximal function of Hardy-Littlewood. Now, we explicitly observe that the Morris space that we have considered were defined in an open-bounded set, but sometimes it could be necessary to consider not in omega but in Rn the Morris definition. So For this reason, we just briefly show you what means what change in the Morey class of Rn. Means that B is not Bx rho, but only B rho, and the supremo is not for rho between 0 and the diameter of omega, but only rho more than 0, because the diameter of omega is the diameter of Rn, so it's plus infinity, of course. So the next result that we would like to show that is a usable instrument for technical regularity results is the following one. Let us consider P between 1 and infinite, more or equals 1, and lambda between 0 and n, strictly more than 0, strictly less than n. Well, in LP, we have that the norm of MF is less or equal to the norm of F in the same class LP lambda. Well, in the weak case, L1, we have that the weak class in L1, we have here the measure of the level set of MF where is more than P cap Pxr is less or equal a constant over T, the radius with exponent lambda, the norm of F in L1. And therefore it means that MF is almost everywhere finite in Rn if F is in LP lambda for every P more or equals 1 and lambda between 0 and n. Let us give a sketch of the proof of it. So we start with this trick, we can say. The integral n of mf multiplied by the characteristic function key could be considered in a useful result proved by Pfefferman and Stein less or equal f and the maximum of the characteristic function. So the maximal is considered to the second function key. So now f and key are two summable functions, and we fix now who is key. Key is for us the characteristic function of the sphere bx0 rho, where x0 is in Rn and r is more than 0. Now we have, so from this, that because of key is the characteristic function, the integral is not in Rn but in B r x0. This is less or equal the same quantity in the second member. Well, so from this we copy the first line and we have that we use the so-called onion method, that is to share Rn in an infinite quantity of sets precisely. The first integral is b to r, so the radius is to r, and the summation of the others from 2r to the others where we consider as a sort of onions Rn. Indeed, x minus x0 is between 2 with exponent k r and 2 with exponent k plus 1 r. In this case, so we have the first quantity is less or equal the absolute values of f in LP. Then we point out that it's possible to prove this inequality thanks this is given by Pfefferman and Stein. Then what we have? We majorize here this quantity in the fraction, and we have that is less or equal 2 with exponent k minus 1 r with exponent n. And if we consider Rn up and down in this fraction, we have only this quantity here. Now we need here to have the norm of f in LP lambda. So in the second member, we have to multiply and divide for rho with exponent lambda. For this r with exponent lambda, so for this necessity, we have up r with exponent lambda And also here in the first term, we have a constant C and the norm of F in LP lambda. Then what we have, because of the series is convergent, is a number, then we have exactly what we need. R with exponent lambda multiply the norm of F. So then the first inequality is proved. To prove the second one, we have that from this inequality that we considered before, and P equals 1, we have that the measure of the set where the level of the maximum function is more than t multiplied by key is less or equal mf key is less or equal the integral in Rn of this last term as in the above line. Then we have that the first quantity here is less or equal if we consider here first and last, we have this inequality. Then, because of key x is the characteristic function of the ball BR, we have that we can majorize similar to before in the case I, and we obtain exactly the version of this quantity here. Well, now we have proved this, we have recalled this fractional maximal result. Then we have a similar one that is the following. If we consider m eta, we have that m eta f is in LP lambda is less or equal the norm of f in the same class LP lambda. So this is an optimal result in the sense that we have P lambda in the first member and P lambda in the second one. But if we consider that now we can call, of course, here Q as this one, then we can consider another result that is considering P sharp, and we have also here not used Q, but P lambda and P lambda. So we have other instruments to majorize some classes of operators in the Morey class LP, in the Morey space LP lambda. Then another useful result is the Ritz potential. Let us consider alpha between z and n, f a measurable function such that is in LP for some p more or equals 1. So we say fractional integral of order alpha or Ritz potential of order alpha, the integral I alpha that is defined here, where we point out that is the down n minus alpha. If alpha is equals to, we call it Newton potential. So let us now study the behavior of this Ritz potential in the following result. So we have that I alpha is less in Q lambda is less or equal the norm of F in P lambda for suitable P and lambda that of course dependent also on alpha. So also, this relationship is an estimate in the Morey classes. If we have P more than 1, we have this. If P is equals 1, we have the L1 lambda version of it that is shown here. Then another user for singular integral is the Calderon-Sigmund singular integral that we'll now define. Let omega x a real function, measurable, regular out of the origin, homogeneous of degree 0, such that is through this inequality, and also that is proven this is considered satisfied this inequality here. Well, for every bounded function having compact support, we define Tf as the limit if x tends to 0 from the right and eta tends to plus infinity of omega x minus y over the absolute values of x minus y with exponent n in this set here where the absolute values of y is between x and eta, then it is nothing else than the principal value in Rn of the integrand function that we defined before. Well, This is the Calderon-Zygmund singular integral. Let us now show you the theorem that is only announced because the proof is nothing else similar to before using Held inequality, that we have Tf in LP lambda is less or equal F in LP lambda. Another operator that is used to compose the solution of partial differential equation are commutators. Di Fazio and I obtained this result concerning commutator. Let us now define what is a commutator and then the estimate. Let us consider alpha between 0 and n, p between 1 and n over alpha, and lambda not between 0 and n, but n minus alpha p, and 1 over q is equal to 1 over p minus alpha over n minus lambda. Let us fix kx as the absolute values of x with exponent alpha minus n. Then the commutator could be defined as the a multiplied by the convolution of kf x minus k convolute af applied to x. This for every f in LP lambda. So the commutator defines a bounded operator from LP lambda to LQ lambda with the previously defined P and Q, and also we can prove that exists a constant C such that the commutators of K and F in Q lambda is less or equal a constant, the norm of A in B and O, multiplied by norm of F in LP lambda, if F is in B and O. Vice versa is something very similar, because if we have that the commutator is from P lambda in LQ lambda, then A is in BMO. And this is proved in a paper published in Bollettino Unione Matematica Italiana. Considering integral operator and non-invariant to translation, it's well known that the more useful operator in the study of partial differential equation are that one invariant to translation. However, it's useful the knowledge of some operators that are non-invariant to translation. For this reason, it is important for us to define Calderon-Zygmund kernel Kx. Let us now define it. This is a function in Rn minus 0 over R, and we call Kx Calderon-Zygmund kernel if R satisfies the following quantities, conditions. First, Kf is in C infinity n minus 0, is homogeneous of degree minus n, and in the unit sphere over n, the integral is equals to 0. Then, if B is a open ball in Rn and Kxz real measurable function in B multiplied R times Rn minus 0, such that is a Calderon-Zygmund kernel for almost every x in B. The maximum of the derivatives of K of every order from 1 to n is fixed as a constant m less than infinity. Then, if we set p between 1 and infinity, lambda between 0 and n, let f in LP lambda, a in B and O, we define for every epsilon more than 0 that k epsilon f is defined as the integral in the absolute values of x minus y more than epsilon of k x minus y f and the commutator related to it are defined like this, then we have that exist kf and c singular integral and commutator in LP lambda such that tends to 0 the norm of the difference of k epsilon f minus kf and the commutator f epsilon minus the commutator. Then, moreover, exists a constant c independent only on np lambda and m, so independent on f, such that as true these two inequalities. Of course, as a consequence, we have that for the Saracen class VMO, we have that if A is in VMO, for every epsilon more than 0 exists a constant root 0 such that if BR is a ball with radius R such that R is less than root 0, then we have that the commutator in P lambda is, look here, not with the norm of A in BMO, but a quantity epsilon for every epsilon more than 0. So now I conclude my talk showing you all the instruments that we need to obtain regularity results for partial differential equations and system, because the solution of a lot of partial differential equation, for instance, in elliptic form, divergence and non-divergence one, can be expressed as summation exactly of this kind of operators. So if we estimate these operators as we proved in Morey class, we can obtain the estimate of the solution and moreover of the highest order of solutions. So I wish to thank you very much for your attention and to give me this opportunity to have in contact with a lot of people all around the world as I see now. So thank you very much to all of you.
Thank you, Professor Maria Alessandra Ragusa, for very nice presentation, and we have time for questions, if any. Meanwhile, may I have some short question? I guess that you have similar result for more general spaces, kind of generalized Morris spaces, right?
Yes, yes. There are a lot of variants of Morey classes. So, of course, there are a lot of open problems because I proved for the definition for the classical Morey spaces, but because of there are new Morey type spaces, it is possible to obtain new results, and this could be open problem. For instance, Orlich Morey spaces, basic base of Morey spaces, or other variants that could be also object of interest in a future research of someone.
But what about local Morris spaces? If there are any difference, if you just insert instead of this Morris space?
No, it's possible, and a lot of results are continues to be to be true for local Morey spaces. Exactly, the answer is affirmative. It's possible and it's positive, the answer. So it depends where we are, in which space we are, but are true in local Morey spaces.
Okay, maybe some more questions. And let me also ask about this technique that you used. I understand that these commutators you apply for the solution of equations of higher degree, right? So
yes.
It's very nice approach. But you need just commutator, or you okay with semi-commutator? What about semi-commutators?
Semi-commutators really have not.
So you don't deal with semi-commutators, okay?
No, probably because are not in the representation formula of a solution of some partial differential equation that I've used. No, but could be interesting to consider to try it.
Yeah, maybe it also will work for your problems.
Yes, could be.
Okay. Well, maybe more questions, if any. Everything was really clear for
Thank you very much to you,
everyone.
Alexey, and
Well,
all the people that are here with us.
Well, if no more questions, then let us thank Professor Maria Alessandra Ragusa for very nice presentation.
No, thank you to you. Thank you. Oh, thank you to you. Thank you.
It was our pleasure to have you with us.